always love to hear from you. Send us your views, comments, and videos with your name and town to the One Africa TV's WhatsApp on 081-200-6659 or send an SMS to 555. One Africa TV. It just gets better.
Speaking about elements, compounds, and mixtures. I'm not going to go into the chemical naming convention today, though, because that is a fairly big topic, actually, and I will cover that in a different session. So, what is the difference between elements, compounds, and mixtures? Elements are pure substances, and we tend to find them on the periodic table. For example, we have things like iron, sulfur, hydrogen, oxygen, and magnesium. So, green could work. There we go. So, iron is the symbol Fe, sulfur is S. Hydrogen and oxygen, you may notice, this is an H2 and an O2. So these are technically molecules, but they are still considered two pure substances, and they're considered elements because this is hydrogen binding with itself. So it's still just hydrogen, even though they are now sort of grouped up in a pair. Same with oxygen. So these are still considered elements, even though they are a molecule. So these are just the elements separately. A compound is two or more elements that are chemically bonded together. So here is some examples. We've got carbon dioxide. So that is our carbon molecule over there, and there is our oxide, or our dioxide. So that prefix there tells us how many, the di or things like that. But I will go into detail there later. We've got water, which is H2O. So this is two hydrogen atoms connected with one oxygen atom. We've got phosphoric acid, which is H3PO4. Again, you guys don't need to know the symbols. I am writing the symbols down because it shows you that these are compounds. We've got table salt, which is sodium chloride, written like that. So here's the important bit about compounds. Compounds can only be separated by chemical reactions. They can't be separated out by any physical means. We don't have a knife sharp enough to go slice atoms apart or molecules apart or things like that. Okay, so a mixture is two or more elements or compounds mixed together. So here's examples. Salt water. Here we've got some salt and some water. So this is two compounds mixed together. We've got coffee. We can mix rice and pebbles. It doesn't necessarily need to be something that is homogeneous. So here I need to stop and quickly explain something. So here we go. We get two different kinds of mixtures. We get homogeneous mixtures and then we get non-homogeneous mixtures. Okay, so very big words, and here's what they actually mean. Homo means the same. So this is a mixture that looks the same throughout. Non-homogeneous mixtures are mixtures that don't look the same. So, an example of a homogeneous mixture would be something like salt water. You can't physically see the salt particles in the water. This could also be something like milk. Milk is technically tiny little oil droplets called lactate or lactic acid suspended all throughout a water mixture. So it looks homogeneous. We cannot physically see the difference between the particles or the elements that make up this mixture. Examples of non-homogeneous mixtures would be something like muddy water, where you add some kind of soil to water. Eventually it would just separate out. This could also be salad dressing. This could be marbles in a bathtub, just with some water. You can physically see the difference between the substances. Okay. Okay. So let's go back to over here. Okay, so our examples of mixtures could be things like salt water, it could be coffee, rice and pebbles. And the important thing here is that these kinds of things, mixtures, can be separated by using physical means. We could technically use only physical means to separate them. Sometimes it's actually easier to use a chemical mean to separate things, like getting the different gases out of the air. The air around you is a mixture of nitrogen, oxygen, carbon dioxide, and other kinds of trace gases. The easiest way to separate these out is to literally have some of these gases react with something else, and then to use further chemical reactions to separate the gas out again, and then collect it into some kind of vessel. But we can separate them using only physical means by literally cooling it down a lot. So we put it into some kind of refrigeration unit that is powerful enough to make the nitrogen or the oxygen in the air turn into a liquid. The first gas that would turn into a liquid would be nitrogen. So this is where we get things like liquid nitrogen. Carbon dioxide, we can do the same. Carbon dioxide does not turn into a liquid, it sublimates, which means it goes directly into solid form. So this is how they separate out gases. They literally cool down the air until one of them turns into a liquid, and then they can tap off that liquid. So other physical means that could be used is things like filtration, evaporation, sorting things, sifting things, all sorts of things. Separating the mixture would depend upon how the mixture was made in the first place. So if we have a solid mixed with a solid, then we can use things like sorting or sifting in order to get the different parts out. If one of the substances is dissolvable, say we have a mixture of salt and sand lying in a pile there on the table, then we can dissolve this salt in order to get it out of the sand. So those are some ways that we can use in order to separate these mixtures. Sifting literally means that you take the substance and you put it through a series of sieves, one of which is smaller, has smaller gaps than the other, in order to separate out different sized particles. So this would be useful if you had, say, little rocks mixed in with sand or something like that. They use this very often on archaeological digs, where they would take the sand, one shovelful at a time, and then put it through a series of sieves in order to find little bone fragments and things like that. So they use sifting in order to separate out the different components of the soil there. Sorting means you physically take your hands and you sort them into their different sections. If we've got a solid mixed with a liquid, what we do here depends on whether it is dissolved or whether it is in suspension. So what I mean here is dissolved would be something like salt dissolved in water. A suspension would be something like sand in water. So if it's dissolved, then we can use evaporation or distillation in order to get rid of the liquid. Evaporation would happen automatically. We just have to put it in a sunny spot and wait quite a while for all of the liquid to evaporate. We can boil it. Careful when adding heat. Adding heat could sometimes start a chemical reaction. So we can use evaporation, which we can either boil it or just put it in a sunny place and wait for it to evaporate off the liquid. And then we are left with, say, the salt crystals left over in the jar or whatever we use to evaporate it off. We can also distill it. And that is literally what is meant by sort of boiling away the one liquid. You would just be catching the liquid in a still and pouring it off again into a separate container. So distillation would be if you want to keep both the salt and the water from a salt-water mixture. So if we have a suspension, that is things like blood. We have red blood cells and white blood cells and platelets all going together in our blood. So we could either wait for it to separate out, but if it's a substance like blood that can actually go off, you could use a centrifuge in order to separate out the liquids. So waiting for it to separate out, we can literally, that would be our sand and water mixture. So if we have blood, for example, we would use a centrifuge. We could also use a centrifuge with a sand and water mixture. It separates out quickly enough and easily enough that we don't need to go to extreme lengths in order to separate it out slightly faster. So centrifuges are one of the biggest discoveries in science. It literally enabled almost all of the laboratory tests that happen on blood or any other bodily fluids in order to take place, so that they can diagnose illnesses or help treat people. Solids mixed with gases. So an example here would be smoke. Smoke from a fire is literally tiny little ash particles suspended inside the gas that the fire gives off. So this would be the tiny smoke particles suspended inside this carbon dioxide gas. So you could literally catch it in some kind of container if you want. A balloon could work well. And then you just literally need to wait until it starts separating out, until the air inside is still and not moving. Then slowly all of the particles will start sinking down and it would form a layer on the bottom. So then we have liquids mixed with liquids. So here again, it depends what kind of a liquid mixed with what kind of a liquid. If it's a solution, which means the one has dissolved into the other, this is called a miscible fluid mixture, which means it's two different kinds of fluids that mixes into each other. So this could be something like alcohol and water mixed together. They dissolve into each other very easily. So here we could literally separate them out by using distillation. So what distillation does in this sense is you would use a stove in order to heat it up slowly until you get to the boiling point of the first substance. So in terms of alcohol mixed with water, the alcohol will reach its boiling point first. So you would keep it at that boiling point, not go hotter. And then you would collect all the gas coming off, funnel it down through a pipe that has cold water running around it in order to cool it down. And then it will turn into a liquid in this pipe and it would drip out the other end as pure alcohol coming off. This is how all sorts of alcohols are made, like whiskey and so forth. They literally distill the alcohol off of the original solution. So, if we've got a mixture of alcohol and water, we would first evaporate off the alcohol, collect it, and then let it cool down, and then collect the liquid alcohol in a separate container. And then we would continue this for the water. So once all of the alcohol is evaporated off, then you can continue this by separating off the next liquid and so forth until you have pure substances. So if you end up in a pharmacy and you buy something like distilled water, that means that it is normal water, normal tap water, or borehole water, or some kind of natural spring water that they put into a distiller, heated it up so that the water evaporates off, and then you end up with a very pure water on the other side. All of the other minerals and things inside the water stayed behind in the still. So distilled water is actually very dangerous to drink because it doesn't have all of those minerals in it. It's going to absorb the minerals from your body, so you might actually end up getting vitamin deficiencies and things like that if you end up drinking distilled water. So distilled water are generally used for things like science experiments or for other kinds of applications. So yeah. So we talked about distillation. So now the next kind of liquid mixed with a liquid is an emulsion. So these are things like milk or mayonnaise. They look homogeneous, but they're actually a mixture of two substances that don't normally mix. So milk is a mixture of tiny little oil droplets, which is your lactose and things like that, mixed in with water. And it looks completely homogeneous, but if you actually put milk in a centrifuge, you would see all of the oiliness separates out to the bottom and all of the water would separate out to the top. Also, if you just put fresh full cream milk straight from the farm in a big dish, then the cream, which is some of the oil, would separate out to the top. So mayonnaise is a mixture of egg and oil, and it is literally the egg and oil mixing together in such a way that it sort of changes the, not quite the properties of both, but it sort of thickens up due to the fact that you've got tiny little egg droplets mixed up with tiny little oil droplets all throughout the thing. So you could separate out mayonnaise by gently heating it until the oil and the egg start separating out again. You could also separate it out just by waiting. I don't know if you guys ever saw, if you put some mayonnaise on a sandwich, for example, and you left the knife or the spoon or whatever you use to take out some mayonnaise with outside of the fridge, and you just left it there, then it would change color. It wouldn't be that sort of whitish color anymore. It would change to a sort of yellowish color. And that would be the oil and the egg actually separating out again. So emulsions, again, it depends upon what kind of a thing you have. Milk you can separate out with a centrifuge. Then we get suspensions. So this is known as immiscible immiscible fluids. which means it is two kinds of liquids that can't mix together, like oil and water. Or in your salad dressing, those bottles of salad dressing that you buy, you normally have a layer of some kind of oil or something, and then some wateriness, some herbs floating around, something like that. So that would be an immiscible fluid mixture. So miscible means that it is two liquids that can dissolve into each other, and immiscible means that it's two liquids mixed together that can't dissolve into each other. So in case of the salad dressing, if you want to pour it on your salad, you have to shake it a bit and then pour it. And if you wait like 2 minutes, you're going to have to shake it again. So you literally just have to wait for it to separate, and then you can pour off the different liquids. So gases mixed with liquids. Here we get two kinds. We have something like a suspension, which is like mist. You've got tiny little water droplets suspended inside this big gas mixture. So mist or clouds. Clouds is a very good example of a gas and a liquid mixed. The other kind is bubbles or foam. So this would be a gas trapped inside a film of liquid. So here we could maybe blow on it to pop the bubbles, because carbon dioxide tends to pop bubbles. You could literally just wait until the bubbles pop by themselves to separate out the liquid and the gas mixture. So yeah. Then we have gases mixed with gases, which is air, because it's like almost 4/5 nitrogen, and it's got some oxygen and all sorts of things. So here we could literally, by physical means only, cool it down until one of the gases becomes liquid. This is how we get things like liquid nitrogen. Okay. Is there any questions for me so far? Because this is pretty much the end of where I wanted to reach today. Let us begin. My name is Christine, and I'm going to be your science teacher, at least for now. So let's see. I want to do pressure and density today. So let us begin. Okay. Here we go. So pressure is the amount of force that is put into a specific area. So what this means is this is how hard something is pushing against a certain surface. So coming back to over here, if you try to put your hand like this, right, and you try and push on it with your whole other hand, that doesn't hurt. It's not that bad. It's fairly fine. But if you try to use something sharp like a pen and you put that same amount of force on it, it hurts. And that is pressure. So getting back to over here, we have pressure, which is a certain force in a certain area, just like your hand and the pen. So we measure it in newtons per meter squared. Okay. So a small pressure means that we have a force that is spread over a large area. So if we look at snowshoes, these are these fairly interesting kind of shoes, where if you put them onto your foot, then they spread out the weight of your foot over a very big area, which keeps you from sinking into the snow. Now, a washer around a nut, if you turn a nut into wood or something, that spreads the force from the nut so that it doesn't push against the wood on these lines over here, so that you don't damage the wood. So that will keep a washer from pushing into the wood, so it spreads out the force over a bigger area. If we look at the other side of the equation, if we look at a knife, then we're pushing all of the force that we're using to cut something onto this tiny little area just there at the edge of the knife. So that allows us to cut a lot easier because we have a great amount of pressure. This is also why wearing high heels is very bad for your health, because all of your weight, all of the force that is pulling you down to the earth is resting on your heel. And this does quite a lot of damage to your ankles specifically, and also to floors and things with soft surfaces. This is how you can literally sink into muddy soil or something. So I talked here about weight, so let me quickly give you the formula for weight. Our weight is our mass times 9.8. And this 9.8 is the gravitational constant. On Earth, it's measured as 9.8. On the Moon, it's roughly a sixth of that. So this depends on where we are in the solar system. So on Earth, we've got 9.8. Our mass is measured in kilograms. Okay. And our weight is measured in newtons. So now, let's move on a bit. So, if we want to work out something using our pressure formula, then we can use this triangle over here. So how it works is, if you want to get the force, right, then you would put your finger over it and close that whole area up. And what's left will give you the formula for force. So force will then be equal to pressure times area. But if we instead want to work out area, then we will put our finger over it and block out A, and that will give us area is equal to force over pressure. So we will get A is equal to F over P, like that. Okay, so let's go do a few examples so that we can get into the swing of things. So, if a man weighs 800 newtons and the area of both of his boots is 0.8 square meters, what pressure does he place on the ground when he stands still? So, we have, if we go look at our triangle and we close up P, then we get pressure is F over A, so force over area. Our force is measured in newtons, and that is his weight. So that is the 800 newton over here, and that is how big his feet are. So if we put that into our calculators and work it out, we end up with 10,000 newtons per square meter. Okay. So this is what a normal man who weighs 800 newtons puts. That's the amount of pressure he puts on the ground. So now let's look at this. A woman weighs 500 newtons, so that's less than that, right? And the area of one of her stiletto heels is that. What pressure does she place on the ground when she puts her weight onto one heel? So now we've still got pressure as force over area, but our force is now